Sure. So I was really pleasantly surprised to meet Dan Aukes on what is technically known as a boondoggle. We were both invited guests at a National Science Foundation The New Makers event in Napa Valley, California. Obviously, there was lots of good wine involved, but a bunch of really interesting people. And so I became fascinated by Dan's work at the time on very low-cost robots that you could manufacture pretty much on a laser cutter. And I've been paying attention to his work for the last few years, and I'm delighted that he contacted us and said, hey, I'm around, can I maybe come give a talk? And so we said, absolutely. And that's what I got to say about Dan. And I'm looking forward to hearing more about his work.
Great. Well, thank you. Thank you, Mark, for introducing me. Yeah, I forgot about that trip, and that was a really neat time, and it was neat to meet all those people. So I'm going to share my screen. I hope everybody can see it.
Yes.
Okay, good. So yeah, and the topic today is how to design more affordable and dynamic robots. And so I'm going to just kind of get into it. First, I'm going to tell you a little bit about myself. Right now, I'm an assistant professor at Arizona State University. I did a postdoc at Harvard and did my PhD at Stanford. So I've been all over, and I've seen a lot of different ways to make robots through those experiences. And so I've kind of tried to create, take what I've learned from all those experiences and really move that in a couple new directions. The lab that I run is called the IDEAlab. It stands for Integrating Design, Engineering, and Analysis. So please check it out sometime. There's more information there, and I'm actually actively curating it these days. So yeah, you'll see more coming online. But I wanted to talk today about where we are with robotics and really what is the goal of robotics. The robots are supposed to be able to design to perform dangerous tasks, work in inaccessible environments. Think about Fukushima, all the motivation for all the funding that came from events like that, as well as to automate repetitive and manual labor so that we can enjoy our lives and work on problems that are tougher and bigger and more challenging. And to do that, they need to be adaptive to new situations, environments, and needs. And at the same time, exceed some sort of cost-benefit ratio. Like there has to be some value in all of those functions. So where are we? How well are we doing? If you take the status quo, a gigantic generalist robot like Atlas, Atlas, hey, this from Boston Dynamics, what you can see, I mean, this is an amazing robot, state of the art. It's great. But there are some drawbacks, and I just messed up the thing. But let's just talk a little bit about some of the drawbacks to a generalist robot. This robot represents multi-million-dollar development cycles. Every time you want to make a design change, you're essentially starting from scratch because you have to reevaluate everything from the very beginning. And so building up a new version, iterating, is a very costly experience. And so when you're designing an expensive generalist robot like this, what you have to do is you have to build every capability that you might want in that robot in at the design time, first time. And so over the number of cycles of Atlas, we've probably seen, yeah, like I said, multi-millions of dollars invested. And so, but at the same time, these cycles grand challenge show that even those generalists have their limitations, right? And this was kind of a black mark for robotics, seeing these videos and all the costs associated with it. And so my goal is to find a different way. Find robots. And so this robot at the time showed that it didn't exceed that cost-benefit ratio to be able to be used in repetitive, menial, dangerous, or low-value tasks. Because if we're talking about menial tasks, it's too expensive to use, especially if it falls over and breaks. I would say that this robot is learning to adapt to needs, and its generalist ability allows it to be used in different situations. But there are other ways to adapt robots for different needs. But I think by far the limitation here is that the research proceeds very slowly and by few people. And that's because the cost of this platform after development is also very high. And so its access is limited to, a couple of research labs around the nation, and that's about it. So how do we gain access to more robots, make these robots higher performing and adaptive to different situations? And that's really what the goal of the IDEAlab is about. It's to shorten the development cycle, increase the affordability, minimize the complexity, and at the same time, increase the performance of niche robots through innovations in design, materials, fabrication, and data-driven decision-making. So how do we do that? Some of the ways we do that is to leverage material and physical intelligence to simplify dynamics and control. And I will go into that a lot, so you'll learn about that today. I'm always considering how we're making the robot during design time. And so that I'm closing that loop between design and fabrication. And you'll also see that throughout many of the robots. We won't be explicit until maybe the third section of this talk. But also very importantly, I integrate real life experimentation data and the physics of simulated robots into the design process as well, so that we can maximize their performance in very niche environments and situations. I just said techniques, but optimization, machine learning, data-driven decision-making for how to select gates to improve, for example, for terrestrial robots, things like that. As well as then adapting these same techniques to be able to teach robots and bring these robots to broader groups of people than just roboticists. Robots aren't supposed to be just for roboticists. So today I'm going to talk about a couple of those things. First, within soft robotics, two topics. One, stimuli responsive material design, and you'll see what a stimuli responsive material is in a moment. And then the second topic, which it's an acronym we've coined in this group of mine, called soft curved reconfigurable anisotropic mechanisms, or SCRAMs. And then we'll talk a little bit about how I consider fabrication in design of robots, and then how we consider the physics of systems when trying to optimize them for niche environments. And today we're not going to talk about machine learning informed design and gate optimization, but we have some really cool stuff on it. So let's just talk a little bit about soft robotics in case you're not familiar with it. The traditional soft robot is a silicone bladder inflated with air or another fluid. It deforms and it creates motion and holds loads through that deformation of the material. And so this is a well-established field that goes actually much further back than maybe people even give credit for. But it is a constantly evolving field. But that traditional vision of what a soft robot is still stands in many ways, because pneumatics still require pumps, reservoirs, valves, and this impacts mobility for mobile robot applications. The second thing is that if you're casting a rubber robot, deforming those stretchy actuators costs energy, and it's energy that you're not performing on the world. The third one, and this has been partly mitigated by 3D printing, but is that fabrication can be messy, inconsistent. It's kind of a dark art. The people who know how to make these things can make them repetitively and with precision, but it takes training to learn. So the access is limited. And then often because of that means that characterization and tuning is often experimentally done, and it's hard to get matched pairs of actuators, for example. And then finally, modeling and understanding these systems depends typically on FEA for complex systems, which can be slow and costly on the computational side. And so some of the solutions that we're looking for across two projects, moving from casting to 3D printing, this is not something that we're innovating in. This is just something that I'm recognizing is happening, even though there are material limitations. Switching from passive to active materials, so the stretchy material itself is doing the deformation rather than a fluidic actuator. Selecting flexible rather than stretchable materials in cases so that you can use more rigid materials that bend only rather than materials that stretch and cost that extra energy. And then isolating that soft or flexible behavior to isolated regions so that your modeling can actually be simplified. You can use some of those rigid body modeling softwares and then connect them with soft connective tissue. So the first way we're doing this is through stimuli responsive material design. And so we're using hydrogels. Hydrogels, even responsive hydrogels, are also well studied but less so in robotic applications. The way they work is that they shrink or expand by passing water in or out of the material itself. But there are many different stimuli that can be used to activate these hydrogels: chemical, thermal, pH, light, heat. We used heat in our application. And there are a bunch of different recipes, a bunch of different chemicals that actually, are collectively known as hydrogels. And so there's a lot of different ways to tune these microstructures to select the recipes. And we'll talk a little bit about that. But there is a big trade-off between the structure and the ability of these materials to absorb water and how tough they are, how strong they are, big trade-offs. So typically the way you see these hydrogels being used in, I wouldn't say robotic applications, but in mechanism design, is they shrink or grow into complex shapes. So if you have a locomoting hydrogel robot, these things move forward by some sort of anisotropic behavior that is a function of their geometry. Often these things, because of the complexity of the material system, they're also activated externally from a light source, a heat source, something in the environment that heats and cools the system as a whole, and the rates of change and the partial differential equations governing all of that determine the forward motion of these mobile robots. So it makes it hard for these hydrogel-based mechanisms to adapt to unstructured environments and respond in a smart way. So that was one of the goals of this project that I've been working on. It just recently ended, funded by the Office of Naval Research. And my role in this project was as the designer. I would take materials from our materials folks and design a system, a platform, and then pass that on to our controls people. And a lot of the content you're going to see here is from a recent paper that was published in Advanced Materials. A lot of the work was done by my PhD student, Rusbek Kodambashi, who just graduated, as well as our collaborators at UCLA. And so one of the things that we did and innovated it that I hadn't seen before is we actually embedded joule heaters within the hydrogel itself. So we created these small little cubish voxels, just millimeters in size, that can shrink and grow rapidly. And hydrogels typically take a long time to expand or contract. And we're able to do that because these systems are so very small. We're just talking about a couple millimeters on a side. Whoop, let's go back here. The other thing we did is we innovated in the material recipe itself. And what you might not be able to see is that there's a hydrogel on the left, middle, and the right. And so what you'll see is, and I'm just going to fast forward here, rates of change can vary drastically across hydrogels. You see the one in the middle, for example, shrunk first, but it also didn't shrink very much. The one on the left, it far surpassed it, and the right, they far surpassed it, but their rates of change were much slower. Now on expansion, that one in the middle started expanding right away and grew quite quickly again. And what we recognized was that material selection really matters for robots. But in terms of actuator selection, you want something that expands and contracts at very similar rates. And that's not something that a material scientist would necessarily think about. They want maximized contraction or maximum speed, but not necessarily balanced contraction and expansion. So we selected, we came up with a recipe where just by tuning water, we could affect the microstructure drastically. And this basically means that the material itself, and this image is coming from our UCLA partners, but what we were finding is we would add different ratios of water at a critical step of our process, and the behavior would change drastically. And what we see here is why. We see that the structure is going from essentially closed cell to open cell, as well as going from hydrophobic to hydrophilic. And right at that transition, we saw a major change in behavior. And so what we're talking about is this kind of point around 0.25, 0.22. We saw changes in the swelling amount, swelling rate, force generated by these systems, as well as the stiffness of these systems. And so what that can do when you take different voxels composed of the same material, but different versions of that recipe, you can create and pre-program, just as we've seen in other hydrogel systems, shapes just based on material allocation. You just put one material here, another material there, and you can create a C, an S, all these different shapes. That's not really the point of this project. Our point was, okay, now the other thing you can do is with that hard-coded pre-programmed material property, you can actually change things like how you grasp and hold onto objects. And so I'll just, you can see here, if you select the right material, you can actually pull a grasped object along. And so you can affect the way, you know, small, soft, active systems grasp and move materials around. But once we have our embedded Joule heater in the system, you can also create responsive systems. By changing the pattern of activation, you can change the trajectory that this goes through. So if you turn it on and then turn it off in the basically forward and reverse in the same manner, it expands and contracts in the same way. If you change the pattern of on and off, so here we turn it on sequentially and then we turn it off sequentially in basically the same way, you can actually create a loop, a hysteresis. You can affect the motion of these things. And that's how we create work on the world through these small little systems. And so just to show the propagation of waves traveling down these systems, we really wanted to show what you can do. This is at a high speed just to show, you know, many iterations of this device. But you can also do longitudinal and transverse waves. So we can really create many different kinds of patterns with these systems. And we use that for just one exemplar application here. I'm just going to move on here. So to move around an object, this is all manual control. You can avoid the object by tuning your orientation as you're moving around, and then push the object going in the other direction. And so this was, you know, connected to we had a little set of slider bars, and we could just control the position and orientation through activating each of the soft voxel actuators that we had embedded. Now we've taken this further. I'm going to kind of gloss over many of these things because in terms of modeling and control, we've done a lot towards understanding how these things move in a system, especially in cantilever beams. You know, we're talking about canonical shapes that can be used in robotic applications. And so I'm going to skip this video. I know we've got a lot to see today. We've also taken these soft voxel actuators and connected them to rigid systems so that we can do things like material transport. So modeling the motion of these things and then controlling the motion of these things has been done for the first time. We used external computer vision to do it with an H-infinity controller. And you can see that we can actually create pre-programmed motion control of soft actuated systems to replicate patterns. And we use that in a payload transport application where we took, and it's very hard to see in the video, so I'm just highlighting it here. You can see a little acrylic plate with a marker on it and 4 of these podia. This is evocative to us of a starfish, of the podia of a starfish. And that's why we, and also when you have a robot that's too heavy to hold itself up, you can flip it upside down. It can move other things like a conveyor belt. So this was our example of how we can use that for conveying material. And I'll just go to the video here and you can see briefly. So you can see the motion moving. This is at 20x. But you can see the little guy moving over, and I'll just move on ahead. And you can see that we're actually able to move that black square over just using this cycle of on-off patterns. Is kind of a quadrature signature or signal there sent to each of those 4 actuators. Now, by tuning the material recipe and really optimizing our design, we also made that system untethered. I have a short video here. Got it going. Now these systems only work underwater. Hydrogels absorb water to expand, and they expel water to shrink. And so we have our circuit board sitting out of the water and our legs sitting in the water. And so you see there's a little water interface, air-water interface right there halfway through the video. And so this thing is able to carry its own weight and pull it up. Actually, these hydrogels are quite strong. Understanding how they are going to move before you design them and make these systems is also really important to us. And so we've done a lot of work in simulating the motion of hydrogel systems and trying to estimate the forces. So this is ongoing work, but I'm just going to show you some cool videos of some of the things that we're working on. Basically, worm-like undulation for soft hydrogel-based robots. I think that's it on the hydrogels. So I'm going to move on to SCRAMs. As I said before, this is soft, curved, reconfigurable anisotropic mechanisms, and we have this is a NSF-funded EFRI project, and so we have a website with actually some cool workshop videos from a workshop we held at Robosoft last spring. So check it out if you want to learn a little bit more, but I'll tell you about our sub-projects today. So what we're trying to do with this project is tune the response of soft as well as flexible systems by just changing the shape, basically changing the curvature of these systems. So imagine a flat sheet, you curve it to look something maybe like a tape measure or a tape spring. The behavior of that material changes drastically, and so you induce buckling, and that's one of the effects that we're leveraging in this project. But we're trying to also identify alternatives to pneumatic actuation or pneumatic-based reconfiguration, so the tuning systems by changing curvature. And I think that, for example, if we use stiffer systems that can still bend, and then you just change the geometry of these things, you can take advantage of some of those goals I mentioned earlier in terms of simplifying the modeling, in terms of keeping things a little bit lighter weight, not stretching the material, but just changing the curvature actually doesn't cost as much energy as inflating a system. And so here's our team. And I'll just move on. I'm going to move on here. All right. So let's first talk about SCRAM beams. So the idea here, as I mentioned, is that you have a tape spring. In the equal and opposite sense, it behaves very differently. If you've ever stretched out a tape measure and then flipped it upside down and it collapses, you know what I'm talking about. And we decided to explore how to control that behavior in a robotic design. And so the first thing we did is we took some tape springs that we fabricated and that we deconstructed from Home Depot, and we kind of just took a look at the stiffness of these systems. And you can see on the right-hand side is when you're pushing against the stiff orientation, the opposite sense. And on the left-hand side, the left hand of the axis, that's the equal sense. And so you can see the behavior is not linear, and it also, that kind of peak here indicates the point at which both sides buckle. And so if you can work in this regime right here without buckling the opposite sense, but perhaps buckling the equal sense, you can leverage some really interesting effects. You can put this into FEA, and you can also understand those buckling limits analytically or with a model. And so you can also design these systems with some knowledge in advance. And what we're looking here to do is to create a new option for how flapping and swimming systems move around in the water or in the air. And so other systems, for example, just flap back and forth and maybe have a flexible system. Others use motors like series motors, so the control complexity is a little bit higher, as well as the weight and the cost. Other systems use joint limits. We're trying to control the dynamics of our system just by changing curvature, thickness, other behavior of that SCRAM-based buckling joint. So I'm just going to show an exemplar video that really highlights how you can control a SCRAM beam to behave very differently. The first case is when you have a very soft buckling effect. This is when it buckles in both directions. Even though it's curved, you're above your, oh, is that, yeah, this is too stiff. Never mind, this is very stiff. It's so stiff that it doesn't buckle in either direction. We're going to go to the next one here. There's too soft to move in either direction. It buckles first, doesn't push itself. And then finally, the Goldilocks situation here is we have one direction that's soft enough to buckle and push it, and the other stiff enough to hold its own weight as it pushes itself forward. And so that's the first example of a SCRAM beam. And so we decided, you know, with this kind of toy example working, we wanted to move forward and see how we can use that in fluids. And so we wanted to explore what's the effect of camber, thickness, length of this beam on the behavior of it when flapping through a fluid. So we first constructed an air experiment. What we saw when we permitted the same beam to buckle or not by basically supporting it so it could or couldn't buckle is we got very different behavior in terms of the forces that we observed, the torques that we observed over time, as well as the kind of the torque displacement and speed this speed velocity curves. So what you see in the orange here is a relatively symmetric looking plot over zero. So what that means is that the work loop, the integral of that, is basically not performing work on the world. It's generating just as much force in one direction as it is in the other. The blue, however, this straight line, this straight segment here, shows off that you hit a buckling limit and the system is not able to support any loads higher in one direction. And so when you take that integral, there's much more area on this side than the other. And what that means is that you're pushing at a higher force in one direction than you are pushing at a lower force in the other. And so what we see, and I'll just move on to the video here. I'll turn off the audio. First of all, we're using simulation or modeling to understand that. I'll come back to that later. We then put that in water and tested that and observed the exact same thing we saw with our peg toy robot, as well as in our simulation. Then we put that in our tank in the lab, and then we put it out in the water and saw it moving forward. So we're able to see, and then we can, turn one on, turn the other on, do things like turning. So it's a really cool result, but we wanted to say in our next paper, how can we control curvature or control buckling so that we can switch our function on demand? And so we added a little, support so that we could extend or retract the support so it could either buckle or not. So instead of a manual support, we automated that part. And the behavior of the same beam when it was supported or not supported, it shows very different stiffnesses. One is more nonlinear than the other. And actually the short beam is quite linear in this small region right here. And so we can get either linear high stiffness or nonlinear low stiffness and with buckling. And so we decided to take advantage of that by, saying either we're buckling or either buckling or not. So we can, for example, turn one fin on and flap like a fin, or we can turn both on and do something like the breaststroke. So we wanted to try and see if we could do that, as well as combine those modes in different ways. The only thing I want to show you here is just how close our simulation is to our experiment. We actually used a rigid body simulation with a nonlinear spring model and a flat plate model for the aerodynamics of the system, which is not intended to be super perfect at the size that we were working with, but it was sufficient to get us very good, within 10 to 15% performance in our simulation versus our experiment, which meant that we could qualitatively optimize our design and then take it to the pool and observe that it was behaving similarly. We also then integrated machine learning or an evolutionary algorithm to, in simulation, find the best design parameters. We then actually implemented that same evolutionary algorithm in our tank in the lab to identify the right gate parameters. And there's a video here, so I'm going to just show you this. Here's the final video. Here's our setup. You'll see the whole thing in the video.
This is the support.
And I'm going to mute that. So I'm just going to scan through this really quick. So again, you see that theory of operation here. Here's our simulation going. Looks like a frog swimming through the water. So on the left, you can see our initial orientation and length ratios of our paddling system change as it migrates through this optimization. So, and that was using simulation. Here's an example of our mechanism going back and forth, so we can either support or buckle. And it used only one motor to do that, which was pretty inventive of my PhD student, Mohammed. Our lab setup consisted of a rail and a position measurement with an OptiTrack system, and then some force sensing when we were fixing it in the water, so we could measure either the torque, the thrust generated, or we could observe how fast it moved. And we used this setup in an automated fashion, thousands of cycles, to identify the right gate patterns to use with this particular design. And so we could repeat that anytime we made a design iteration. And finally, I just want to show you the result here and how close it looks to the simulation. And the simulation was done well in advance of the actual experiment. we were just blown away at how close it looks. But what you haven't seen is it switching. And so we can also engage that buckling limit. And I'll just show you here. There's my favorite one. We lock one, but not the other, and now it behaves like the tail of a fish. And so you could consider all the different combinations. You could go forward. If you change the curvature or reconfigured the buckling beam in the right way, you could even go backward if you had a different system. And then you can go left and you can go right without turning. You can do all those things in theory. And here's a kind of a wiggle. You'll see some simulated wiggles later. So those are our SCRAM beams, and that's how we're working with them, how we're using them. I also want to tell you a little bit about SCRAM tubes. So if you think about a paper towel tube, you know, once you finish the roll, you pinch it in some orientation, and it suddenly turns from a structure to a mechanism. And so we wanted to see if we could leverage that. So basically, yeah, if you pinch a tube, you initiate buckling, and that creates a virtual joint. If you do it in a soft material, it also can be recovered. So what that means is that you can select the location and orientation of joints on demand in these kind of soft SCRAM tube systems. When you release it, if you pick the right material and you've designed it right, it recovers its original shape and it doesn't deform it or create too many creases in the system. And so what that means is you can create joints on demand in any orientation. And so we wanted to see if we could do that. We created some initial prototypes. On the left, we used the plastic you see there is actually PET from a water bottle that we kind of attached to two 3D printed rings. And we went up in quality a little bit when we moved over to, I think it was a TPU rubbery material that we were able to 3D print on our 3D printer. And this is simply showing that we can deform and pinch, and the pinching force creates that nice deformation. Once it's pinched, we wanted to see what's the difference in stiffness between our structure and our mechanism when it's pinched or unpinched. And so you can see when it's pinched, you have a very low stiffness joint. When you're a tube, it's a much higher stiffness. And so you can select between these two behaviors just by pinching. The other thing you can do, and this was done in FEA, and then we did it experimentally, is you can mix the pinching forces on the exterior of the cylinder to control the orientation of that joint axis. And so in FEA, we were able to mix a subset of pinch forces to create the whole 360 or actually 180 degree range of angles that we needed to be able to generate pinch angles in any direction. In experiment, we used that with a set of 3 tendons that were mounted externally and pulled 1, 2, or 3 to show that. And at this point, mixing those 3 forces was very difficult just due to the motor selection and a couple other kind of limitations. But we feel like we would be able to mix those forces to actually pinch in all directions, not just the 3 principal directions. And I'm just going to show a quick video here right at the end. So you pinch, oh, this is recovery. Here we are. So when you pinch in those 3 directions, you get very different deformation once it's under load. The one that's oriented with the weight deflects the most. The one that's at an angle deflects down into the left, and the other one deflects down into the right. And so you can use this behavior to actually get very different behavior. The one thing here is you can see we also implemented active recovery. So you actually pinch the other 2 tendons to pop it back even under load. You can recover that original structural shape. So there are ways of recovering that tubular shape even when it's under load. So we think that this could be really useful in snake-like robots, robot arms, parallel mechanisms, any system where you want to be able to reconfigure and redefine your mechanism on demand. And the next application is where we combined tubes and beams together to create a little mechanism that actually propagates curvature from a pinched tube to a buckling beam. And I'm going to just go right to the very end. You've seen a lot of examples of this already. We have our force testing, we're doing simulation, We're getting out the stiffness profile in positive and negative directions. And we're using that to get very different behavior. And I'm going to mute this here. So I'm just going to go to the very end. And what you can see is when you inflate this, this is a very traditional inflatable actuator that just simply deforms our tube. That propagates the curvature, though, to the buckling beam, changing the curvature of the beam, changing its buckling behavior. And so in one direction, you buckle, and in the other you don't. Basically, you're able to push forward, and then it buckles when it comes back. And we have some simulation to show it. What we found also was that we had to add these little extra rigid fins on the end because the forces weren't high enough to actually buckle it. And so our simulation also supported that. Without the load fins, there was almost no difference. The system didn't buckle, but when you added extra drag on the system, we were able to ensure that the system buckled in one direction, not the other, creating that same breaststroke-like motion that we saw in earlier videos. So this funding is provided by NSF, and it's a EFRI grant, and it's an awesome project that I'm really happy to work with the people I am. The next thing I wanted to talk about briefly, and I'm going to keep it really short because I want to talk a little bit more about modeling and simulation and how we use that in designing our robots, is how we're using voxel-based design approaches to capture material properties and then to use those in 3D printed and other 3D applications for CAD modeling. And so the long and short of it is, if you saw my talk 6 years ago at the Atlas Institute, you would know that I did the same thing for flat laminate designs, considering the materials of each layer, 2D laminate manufacturability algorithms. And what we've done here is we've done basically the same thing with multi-material, gradient, and other types of 3D representations of boxes. And this is meant to be paired with some of the hydrogel stuff that I showed you earlier, as well as 3D printing compatible materials. And the reason we want to talk about this is because if you have multi-material systems or multiple parts, let's say you have an embedded part that you want to 3D print something, embed a part in another, take an off-the-shelf part, put it in. How do you plan around multi-material processes across potentially multiple machines? So this tool, Voxel Fuse, allows us to take those material properties, encode them in the shape, and then transport those along in the design process so that we can actually compute manufacturability of the final design and then compute how to make it. So I'm just going to skip ahead and show an example here. So here's a case, and you see a white and a black 3D printed portion. The white portion was printed after an inserted part was put in. And so all of this was computed by basically saying we have a 3D printed shape we want to produce. We have an insert that we want to produce. Tell us how to slice it so that we can insert that device and then keep printing without interfering or hitting that inserted part. This is just one example application of how we envision using this. There's another kind of example here, and that's for generating, I'm just going to go back here, generating interfaces in terms of multi-material or graded interfaces. Often gradients are one way of mitigating stresses in multi-material systems. If you have a hard boundary between material A and material B, that's typically where the material system breaks. And so by enabling gradients, you're actually reducing the stresses in the transition between material A and material B. A lot of people do reinforcing material between those materials, or a dog bone shape, a mechanical lock. And then gradients are another way people have done it. What we're doing is we're taking that voxel-based design approach and mixing materials in different ways so that they're compatible with lower cost and affordable 3D printing solutions. And so we investigated all these different types of patterns between like blurs, which you can print on a polyjet style machine, but other things like dithering and lattice elements and periodic surfaces, as well as bio-inspired patterns like a fiber pattern that you might find between a tendon and muscle. And so we printed all of those and compared their performance and their force limits and their stiffness, tried to normalize their stiffness together. Found a lot of interesting things. This is work that's right now in progress, and so in review, or in revisions. So more to come on that. But I just wanted to show you, we're taking these material systems into account during the design process. And then finally, just wanted to briefly touch on model-informed systems design. This is how we're doing a lot of the work that we're doing in SCRAMs and soft robots, but we're also applying it to a lot of the origami-inspired robotics that I've been doing a lot longer. And so just some examples of model-informed design processes that we've done. We've done jumping robots, gliding, flying, laminate, other types of laminate systems. Here's an example of a jumping robot designed by an undergraduate student. It's going to take a second to load. It always does. He went through this process of modeling the motors, the inductance, the resistance. He did everything, the stiffness of each beam, and encoded that into the simulation, and was able to optimize his design in simulation and actually obtain very, very similar qualitative curves when he made all these different iterations of his jumping robot. And he was able to balance the design needs between jump height of the body as well as jump height of the foot, and balance those and trade those two things off so that he could get a design that both jumped itself high but also lifted its foot off the ground. Oops. Jump gliding. Here's an interesting concept. You jump up and you glide down, and that's to save energy that you generated during the ballistic phase. We wanted to take a SCRAM-based approach at this, and so we took our buckling beam, attached it to two flat plates, and then I had another honors student, measure the drag over many different cycles of testing. I'm just going to move on. Created a launcher using an inflatable 2-liter bottle and a bicycle pump. These are all different tests, all of these. And then he was able to observe a lot of interesting dynamics here, which one of my master's students was able to simulate using two different methods, a flat plate approach as well as a Vorlax, a vortex lattice code that he integrated into the simulation, to get very, very similar qualitative results, which we hope to use, for other fluid-based applications. I've done a lot of origami-inspired designs, and so modeling the dynamics of these systems is really important. Here's some work we did modeling the dynamics of closed parallel mechanisms. In terms of terrestrial locomotion, we're studying how designs and stiffness can permit bipedal walking, jumping, landing. And we're using this for an upcoming project I'll tell you briefly about, but also we're using it for fluids rather successfully. So that's that wiggle that I was telling you about. That's the gate that we found. Yeah, we're able to qualitatively get very similar trends, even if we're off by 10%. Our designs are much faster. Our simulation is much faster when we make approximations like this. And so what that means is that we can find and optimize systems in simulation, and actually simulate these systems almost as fast as we can make them, because we can make them just as fast as we can simulate them in some cases. So it means that we have a very tight integrated simulation and fabrication loop. But when we need to, we can integrate FEA into our simulations. And so on the left, you see a soft element here. On the right, you see a rigid element. And you can get very different behavior in jumping applications, for example, when you consider and include the sometimes detrimental performance of affordable material systems into the design process. And so here we're saying, what if you have cardboard to work with? How about we tune the design of our robot to match the stiffness of the cardboard rather than assume that everything is rigid? And that allows us to make higher performing robots. And here's one more example, a SCRAM-based swimming robot in water. So we actually can observe different forces in one direction than the other just by encoding that curvature in FEA and combining that with fluids. So I'm applying all of this stuff, this modeling and optimization in my career project to basically create lower cost, more affordable robots that you can make faster using origami inspired techniques, as well as some of these other soft robotic techniques. And trying to tighten that loop between, instantiation, simulation, optimization, going back quickly. We can make our robots in minutes, these origami inspired robots. And so what that means is that we can often experimentally understand how they're going to work faster than we could simulate it with a full fluid simulation. So we need to pair these things together, use them appropriately. Other projects I'm not going to talk about, wearable robotic suit that we're using origami inspired techniques, a swimming robotic fish that used a 5-bar spherical mechanism that was origami inspired to swim in a canal. And I'm not going to show that video because I want to take questions. So check out my lab's website. I'm, like I said, constantly curating it, and I'm trying to include more information there. Our ScramBots website. Thank you to all of my PhD students. We had our first 2 graduates this spring, summer, and so, and then also in terms of the projects that I've worked on, a lot of co-PIs have helped in many of these cases, so it's not just me pulling the load, as well as a lot of close collaborations with students on some of those projects and my students. So yeah, funding, and that's it. Just wanted to get done before the end of the hour.
Woo. Dan, that's a lot. That was a lot of information.
Yeah.
You've been productive.
Yeah, it's fun to go back and look, and you're like, whoa. So sometimes you just lose all of it and forget it. So
there's a comment in the chat from Wayne. Wayne, would you say it?
Oh, sure.
Oh, no, this is really cool. I'm just wondering where you get the inspiration for these particular structures. Is it, I think, as Mark was mentioning, from the natural world? I picked up a tape measure, I picked up a toilet paper roll or a paper towel roll and say, wow, this is kind of amazing.
Yeah.
And the flapping stuff reminded me of this product from Hobie, which is pretty old now, but it's a really efficient way to propel your kayak or pedal board.
Yeah.
And I don't know if they've modeled it. I don't know if they'd be interested in improving the way they do it based on what you guys have learned. But it's like, yeah, you think of an oar or a propeller, but these guys said, no, let's think about fish.
Yeah, no, I'm familiar with that. I actually just saw it for the first time like a couple months ago. And it's, yeah, very evocative of fish and very organic looking. And I think that trying, for me, I'm always trying to take the motors out of the system and encode that into motion that I can generate with a really interesting shape combined with the right material, because the cost of adding that motor, controlling that motor, sensing that motor, and then really actually knowing what to do with that motor, making decisions about what to do, there's a cost to it. It means you go slower in your development cycle. It means the resulting robot's more expensive. And really, I'm motivated, and I am looking organically, I'm looking at the natural world, because these systems solve problems by factoring the material, the shape, everything into account, rather than by just simply adding another joint or another muscle. So it's really just constantly asking the question, how can we take that motor out and replace it with a spring, or replace it with an interesting spring?
That's great. Very, very, got my head spinning. Thank you.
Well, I had 2 things to ask. One is that in the first segment, the hydrogels piece, some of your videos were sped up a factor of 50 or 80.
Yeah.
So could you talk a little bit about speed?
Speed is a huge factor, and it's you saw some of the single voxel videos, and you saw that it was actually able to deform in real time at the speeds that we would really want it to. Hydrogels themselves are ultimately limited by just the physics of, expelling water through the material itself. The trade-off of having a more spongy material that can expel water and has more surface area means you have a softer material. And so when you need to make it stiffer to hold its own weight, suddenly everything goes slower. If you make something bigger, the volume to size ratio really dominates, at anything more than a couple millimeters. So these robots are limited to water and very small scales, but there's still a lot of interesting problems that can be solved in small scales in water. And so I think thinking about different applications rather than trying to lift something big is where we would want to go with a hydrogel-based robot, until the material systems catch up.
No, totally. I mean, it's exactly as you said, finding the applications that suit the characteristics of the system rather than trying to make the system do things that it just doesn't want to do.
Right.
The other thing, some of your simulations are amazing, and I wondered whether the simulation tools, whether you have a suite of simulation tools that others can use.
Yes.
If we had people who wanted to do that, how would that go?
Yeah, so today you saw primarily 3 different tools. One is a package I developed in Python called Pynamics. It's really, really straightforward, basic rigid body kinematic or dynamics. It doesn't do a lot of things very well, but it's written in Python. And so it represents the equations, it generates the equations of motion. You can see the analytic expressions, even if they're complex. And you can work with those, adding constraints, adding point contact, wherever you want. And from a scripted approach, it's my workhorse, how I understand things before we spend the time developing an FEA model, before we spend the time adding fluid dynamics, because it does so much, and it's capable of doing the basics. Where it's not good, we move to other tools. One of my exciting ones that I really like these days is Chrono. It's an open source tool that has discrete elements, so granular media support. It has FEA built in. That was that jumping FEA-based robot you saw, as well as contact handling. So when it comes, and it's Python compatible as well for many of those packages. So maybe not for granular. You need multi-core for that. But we've been using it to relatively good success when we need it, because there still is a cost to added complexity. And then the final one, Voxelize, it's actually a family of softwares. There's lots of different branches of it developed by different universities. We adapted it ourselves to factor in the hydrogel dynamics. So the response of hydrogels and all of our different recipes, we encoded into specific voxel types and allowed different voxel types of our own custom design to be inserted into the Voxelize engine. And so the Voxelize is another good one that's out there. I would say that one has some ultimate limitations that in terms of estimating forces, it's the way it simulates isn't super compatible with identifying the forces required. And so some of the nice hydrogel simulations we saw are ultimately going to be limited in what they can help you understand. So, but try Pynamics out. I teach foldable robotics. I teach this class that I created called Foldable Robotics, and I use Pynamics in that with 4-bar linkages, and students create their own dynamic origami inspired robots, and then they optimize it using kind of the same approaches you saw for the jump gliding, for the jumping robots. And so let's see, I will paste in foldable-robotics.github.io into the chat window, and you can go there and check out some of the course notes that I have posted. A lot on simulation, manufacturing, a lot of the origami inspired design is encoded into that class, and that's what I teach, and I'm teaching that in the spring.
Dan, there's a question in the chat for you.
Which backgrounds do my PhD students have? I have so far hired people who have a broad mix of mechanical engineering and systems engineering, I would like a computer scientist. I would like someone who is very comfortable in fabrication and materials. But it seems right now my students are generalists, and so they're good at many things. But I haven't specialized in my selection because each of the projects that I talked about requires someone who can wear many hats. And so I kind of, I haven't been diversifying the skill sets. But I would say as my lab grows, that's exactly what I'm going to be doing. I'm going to specialize in who I hire to work across projects rather than a generalist on every project. That'll probably be one strategy that I go for. But so far, I'm a mechanical engineer. I need people who can understand dynamics, who know how to fabricate, who know how to use ROS. So there's a mix of computers, programming, a lot of Python, and mechanical engineering expertise. So, yeah.
Can you quickly describe the fabrication process for the hydrogel robots? Like, how do you make it more faster, more streamlined? Since I've done hydrogels before and it took such a long time.
Yeah, so that's actually one of the recipe that we used is a standard off-the-shelf recipe with like precursor solution that you buy from a standard chemical manufacturer. The casting process is described in the paper in brief, but basically we're casting. We're not spraying. We're not 3D printing, and so we make these little molds. We have a fixture to embed they're just SMD resistors, surface mount resistors that you would put on a surface mount PCB. And so we pre-make those. We kind of align them, put them in the mold, pour in the solution, and then UV cure it. And so the UV curing, the use of really off-the-shelf materials, we're not a chemicals lab or a materials lab. We were able to do that in our fume hood. We do have a fume hood though. We were able to do that in our fume hood without assays of all these different materials, without heating or cooling or cryo freezing, any of these really specialized activities. So we just got a really nice UV light and off-the-shelf materials and tuned just that one property, water. The percentage of water in our recipe was enough to change the microstructure. And so that's what we did. We tried to keep it simple because that's what we have available to us,
I guess I missed it, but I wonder what's the actual trigger for your current hydrogen actuators, just which approach.
Yeah, so ours is a thermal responsive P-NiPAM hydrogel, which means that our little surface mount resistor, which is embedded in each voxel, as soon as we pass a current through it, it heats up and the system shrinks down. And so it passively cools. And the idea would be we need to find designs that actually are open cell designs that permit water to pass through the structures that we design, rather than to make it just a solid volume of material. And so that is one design criteria we have to think about, is how do you create networks of hydrogel voxels that permit water to flow through the system to keep everything cool, to passively cool on demand. We also actively cooled with the water, but yeah, we envision this to be used in the real world out in the ocean and at temperatures where P-NiPAM could passively cool by itself. So this was an ONR funded project, right? So Office of Naval Research, they want something that works in seawater. So this is actually pretty perfect for them.
Cool. My research is about on-body haptics and this kind of actuator. So I wonder, is there any possibility to use hydrogen in any on skin or on body kind of applications? Yeah,
I mean, the cured hydrogels are usually more inert than their precursor solutions. There's probably some more toxic substances when you're mixing it than after it's cured. But many hydrogels are targeted specifically for in vivo applications. And so if you selected the right hydrogel, they're actually well suited for working with the human body. I'm not exactly sure about PNIPAM itself in its cured state, but you know.
Yeah, thanks. Really sorry.
Yeah.
And also for the simulation, like I only have design background, and I just saw like one of your, I guess, master students' work. Seems like just the Unity environment. So
Yeah,
like,
yeah. So he used Unity, and that was a pretty good experience. We liked it. We were using discrete rotational pin joints when we wanted to represent the compliance of a flexible beam. So we didn't add any soft materials to that, but it was a good enough representation, and it matched the stiffness profile of the beam itself fairly well. So yeah, it's programmed in C#, Visual Studio. It was a fairly straightforward experience. I think the downside for Unity, the upside is that there's a lot of support in the gaming community. The downside is that it's more of a black box in how it works. And so you don't necessarily know what the trade-off is between precision and accuracy and quality of the simulation versus speed. So it's not necessarily a limit we hit. So that's not necessarily a concern right now, but it's something to just be aware of. Is you have to know what's inside the black box sometimes. Cool. Well, thank you guys so much for hosting me.
Thank you.
thank you.
That was good. That was great.
Cool.
I hope
Well,
to see you in person in the future. Huh. Yep.
yeah, I mean, I'd be happy to, please send me an email, and I'm happy to answer any other questions if you think of them later. So, yeah.
Cool.
And if you come to Phoenix, it's wonderful in the winter. Please stop by the lab, and I can show you some of these things in person. I think that would also be really fun. So, yeah, one of the reasons why I reached out to everybody and saw if I could, give a talk is just because past 2 years are hard for collaboration. It's hard to keep that network and the community going in robotics and engineering. And so please come visit.
Yes.
Yeah.
Okay.
Okay.
Thank you.
Thank you.
All right.
See you guys later.
Thanks a
Bye.
lot. Bye, everyone.
Thank you. Bye. Thank you, Ren.
Bye.
Bye.
Bye. See you tomorrow.
All right. Bye.
Bye.